Hello everyone, here is the video for chapter 7.2 on sampling distribution of means, and the next video that I'm going to put up after this one will be for 7.3 that deals with the sampling distribution for proportions. I'll give you a brief intro before I do examples with you. So in chapter 6 we had the normal distribution, that's in 6.2, and we know what that looks like. It's a symmetric distribution about the mean, and you can use the normal distribution table to do calculations based on it. Now here, what you are dealing with in this picture I have here is a data set. There are 8 data points in there, and you can see the histogram for the data set, right? The histogram for that data set is sitting right beside it, right? You can see right here. It's not normally distributed. Now, can we do something with that data set so that we can use the normal distribution to do calculations on this data set? Turns out that we can do that, but we would have to make some adjustments, and the adjustment is as follows. So if you take samples of size 2, which is what I have right here, bottom left, right? You take samples of size 2 from these 8 data set. That means, and the samples you're taking are such that you can they are with replacement. So that means you can have things like 54, 54, 55, 55. That's a sample of size 2. And you do that for the data set, you would have 64 in the sample. 64 pairs in the sample is what you're going to have. That's what you have right here. And then you take that the samples you have, and you take the means of each of the samples. So take the average. So for example, 54, 54, if you add those two things together and you divide by 2, you will get 54, right? If you do 54, 55, and you add those two things together, you will get 54.5, and so on. That's what you have here. So you have 64 means in there. Now redraw the histogram. The histogram looks like this now. The only thing is that on the x-axis, you don't have the raw values anymore. You have the means of the samples on the x-axis. And the distribution is now normal. You can see that the symmetry right about the middle there. That is what the Central Limit Theorem talks about. That if you have a data set that is not normally distributed, or whose distribution you don't know, no problem. All you have to do is take samples of size 30 or more to guarantee that the distribution of means will be normal. And then you can use the normal distribution curve and the table in your formula sheet to do your calculations. That's what the Central Limit Theorem says. Let me read it. If samples of size n are randomly drawn from a population that has a mean, mu, and standard deviation, sigma, the sample means, x bar, are approximately normally distributed for sufficiently large sample sizes, n greater or equal to 30, regardless of the shape of the distribution. If the population is normally distributed, the sample means are normally distributed for any size sample. That's what the Central Limit Theorem says, and that's what we're going to do calculations based off of. So we're going to see scenarios where we don't know the population distribution. We don't know what it's like. We're also going to see scenarios where we know that the distribution is not normal. And then we're going to see scenarios where the distribution is normal, the original distribution. And what we're saying here is that if the original population is normal, right, if the population is normally distributed, then the distribution of means will be normally distributed as well. And the sample size would not matter. You could use a sample size of 2, sample size of 3, sample size of 10. That's okay. The one where your n has to be at least 30 is if you don't know what the distribution is, or if you know that it's not normal. Okay, then you can do that. Okay, so that's what we're going to be doing here. Then the mean of the sample means. So when you have all those sample means, the mean of means, we're going to note the notation for that is mu sub x bar, right? That's what that is. And the mean of means is mu, is the original mean for the original distribution that you have. And the standard deviation for the sample means, which is also called the standard error of the mean, is sigma sub x bar. That is sigma divided by the square root of n, where n is your sample size. Okay, so what has happened now is that we have gone from the original distribution that wasn't normal, which is this one, right? And then we have managed to transform that into a distribution that is normal, which is this one. The z-score we used to calculate in chapter 6 was this one right here. This is from 6.2, but that's not what we're going to use here. The one we're going to use here for 7.2 is this z-score over here. So we're going to transform our means into z-scores, and we'll use our normal distribution table to do calculations for these. So let's do a few examples now. Sorry, there you go. So for example, suppose that the weights of people are normally distributed with a mean of 62 kilograms and standard deviation of 5 kilograms. What is the probability that a random sample of 16 people will have an average weight exceeding 65 kilograms? So what we have to do here is to note a couple of things. First of all, we are told that the weights of people are normally distributed. So that means the original data, not the means now, the original data itself is normally distributed. That is why the sample size does not matter. It doesn't have to be at least 30. It can be less than 30, no problem. That's why n is equal to 16 here. And we know that the distribution of means of samples of size 16 will also be normal, according to the Central Limit Theorem. Okay? So, since we know that the distribution of means is normal, the picture looks like this, and we are looking for, we have a mean of 62 kilograms, and the standard and the mean we are looking for the sample of size 16 has to be at least 65 kg. So 65 kg is over there, and to the right of 65 kg is what we are looking for. We want the area to the right of 65 kg. So we want the probability that the sample mean is greater than 65 kg. The z-score that we're going to use to calculate, to standardize our raw value, is this formula that we have here. I've shown you that before. It's not the same thing as the one we had in chapter 6. It's a little bit different now because you are dealing with a distribution of means. A standard deviation for the population is 5 kg and the sample size is 16. So therefore, our z-score will be 2.4 standard errors. Okay, that's what that would be. So if you use that formula to calculate, you'll get 2.4. And now we will turn our problem into a z-score problem. The probability that the sample mean is greater than 65 kg is the same thing as the probability that its corresponding z-score is greater than 2.4 standard errors, which you can calculate from your normal distribution table, right, from chapter 6. So on the left side of the table, you can look for 2.4, and across the top, you look for 0.00. The area you will see is 0.4918. And your table of values only gives you area between the mean and a specific z-score. So area to the right, you will just have to subtract from 50%, like this, so 0.5, which is half the distribution, and subtract 0.4918. You will get 0.0082, which is the probability that a sample of size 16 will have a mean greater than 65 kg, where the population mean was 62 kg. So it's a very unlikely thing to happen. It's 0.82%. Hope that's clear. Next example, example 2. Statistics Canada reports that the average annual consumption of fresh fruit per person in a recent year is 39.4 kg with a standard deviation of 12 kilograms. Suppose a researcher took a random sample of 38 people and had them keep a record of the fresh fruit they ate for 1 year. What is the probability that the sample average will be between 35 kg and 39 kg? Again, please note that in this example, we are not told about the distribution of this original data. It's silent. Okay, that is why the random sample that is going to be chosen has to be at least 30. In this case, it's 38, which works just fine for us. Okay, so the distribution of means of samples of size 38 will be normally distributed according to the Central Limit Theorem, right? So what we're trying to do is that since the distribution is normal, on the x-axis we have the x bars, okay, which is the sample means, is what we have on the x-axis. And so we want the probability that a sample of size 38, we have a mean between 35 kilograms and 39 kilograms. So the picture looks like this. The z-score for each of the means that we have, 35 and 39, we will calculate using our z-score formula as shown. And the information we need is this population standard deviation, which is 12 kilograms, and the sample size of 38. The z-score for the first value, which is 35 kg, negative 2.26, okay, is the calculation for that if you use our z-score formula. And then for z sub x2 bar is 39 minus 39.4 divided by 12 divided by square root of 38. That's negative 0.21. So the z-scores are fine. So what we're trying to do now is to figure out the probability that the sample mean lies between 35 kilograms and 39.4 kilograms. So to do that one, we will turn that into a z-score problem. That means that we are looking for the probability that the z-score is between negative 2.26 and negative 0.21 standard errors, which will give us, in our picture, all we are going to be trying to do there is to find the area between 39 and 39.4, and then the area between 35 and 39, right? So we'll subtract those two things, which if we do, we'll get 0.4881 minus 0.0832, which will give us a result of 0.4049. So that will be the probability that a random sample of 38 people will have a sample mean between 35 kg and 39 kg. I have one more example for you. And this example is a scenario where the population is finite, okay? The examples we've done so far assumes an infinite population, or a really large population, in the millions maybe. Right? So the difference is that sometimes you would have a population and you know the population size. So if you know the population size, this is how you will do something like that. So let's read the problem. A production company's 350 hourly employees average 37.6 years of age with a standard deviation of 8.3 years. If a random sample of 45 hourly employees is taken, what is the probability that the sample will have an average age of less than 40 years? And I tell you in there to use finite correction factor in the denominator. Excuse me. Generally, I won't tell you that, but in this example, because I'm just illustrating, I will say that. And I'll show you what that means, okay? So the first thing to note here is that we don't know what the distribution of the age of the population is, okay? We don't know whether it's normal or not, and we don't know what distribution is. So our sample size has to be at least 30. That's why they're using 45 in the sample here, which is more than 30, according to the Central Limit Theorem. The other thing to note is that you have a population size that is finite. There are only 350 people in the population, so that's finite. Therefore, we're going to use a finite correction factor, which I'm going to show you in a minute. The distribution, because the sample size is at least 30, we know that the sample means the distribution is going to be normal. The picture is going to look like that. And we are trying to figure out the area to the left of 40 years of age. That's what we're trying to do here, right? And to do that, we know that the distribution is symmetric about the mean. Half of it is to the left of the mean, half is to the right of the mean. We know that 50% is already there. All we're going to be trying to do is figuring out the other part of it, right, from the mean to age 40. We're going to try to figure that one out. And then once we figure it out, we are going to add those two things together to calculate our probability. The z-score we're going to calculate, like we said, is the z-score for chapter 7. But in this case, since the population is finite, there is a finite correction factor. And you can see that the formula is a little bit different from the one I used previously, right? You can see that factor right there, okay? Square root of capital N minus little n divided by capital N minus 1. Capital N is the population mean. Sorry, the population size is what capital N represents. Little n is the sample size, of course. So you have to put that in there to account for the finite population that you are dealing with. So this z-score, therefore, if we use the formula we have right now, will give us 2.07 for the z-score. And then we can calculate the probability of that the average age of a sample size of 45 employees will be less than 40 years of age, which will become a z-score problem. That's a probability that the z-score is less than 2.07. And then from what we showed before in our picture, all we're going to be doing is adding 0.5 to the area between the mean and age 40. That means if you look at your z-score table, it should be 0.4808. So if you add that to 0.5, your result will be 0.9808. That is the probability that a sample size of 45 employees will have an average age less than 40 years if the population age is 37.6 years. I hope you understand. So I have some examples for you to do, or some practice problems. I've chosen a few for you. Please go to your textbook, or go on Wiley online and look for these practice problems, and please work your way through them. And then we're going to put up some assignments on Wiley for you to do as well. So the next video will be on 7.3.